All right, let's get started. So I want to wrap up dimensionality reduction in the next hour or so. There is one other clustering algorithm that's in my slides, which I'm going to share with you, but I don't want to cover here in the lecture because it's just it's pretty straightforward. You'll try to you can understand it, but we'll skip it for the time being, just in the interest of time, because I want to get to the dimensionality reduction. Now we've talked about clustering. Can you give us some reasons for using clustering? So when would you use clustering? Can you think of real problems where you can potentially use clustering? Okay. Perhaps from your own research. Are there problems where sorry? Harvesting, yeah. Can you explain?
Fruit harvesting.
Okay, so how do you formulate? What's the clustering problem?
So like mangoes and stems, like we cut fruits. So we might be having larger size of mangoes, smaller size of mangoes, different.
What is your X?
X can be based on radius of mangoes.
Radius of mangoes are three-dimensional objects, right? How do you find radius?
Matlab sir, like based on image based we can.
Image, sorry? Yeah.
Based on drone images, we can classify big mangoes, small mangoes, and then we can segregate, or we can segregate mangoes and apples also.
I see. Now, okay, I see what you're saying. You have images of mangoes, and you want to classify them into big and small, but you don't have labels. You just have lots of images of mangoes. You want to classify them into different classes. Now, yeah. So let's say you pick two classes. Your algorithm can classify them based on their color, maybe, or size, or something else. I don't know. I mean, because you don't have labels. It can do one of those.
Yeah. This is unsupervised.
It is unsupervised. Okay. All right. Yeah. Any other examples? Okay. Yeah.
Just complementing what she's saying. One is from image. That is from that we'll get to know the shape. There could be other sensors incorporated which tell about the weight of it and color of it and shape of it, like shape she included. Right. So it could be, I don't know, I can say it as three-dimensional. Mm-hmm. Three sensors could be used.
Okay.
Yes, sir.
Nice. Somebody at the back.
So in the distillation column, we have some abnormalities like flooding and weeping. So based on that, we can classify the data in means when the column is operating in normal condition or when it's in flooding or weeping condition.
Right. Yeah, I mean, classification, you need the labels, but if you're trying to cluster, then you don't need labels. Clustering is a very common tool used in image processing as well. So let's say you have images of multiple objects. You don't have labels for those. You just want your algorithm to put them into groups of similar objects. Hopefully, it will do it. But obviously, you have to play around a little bit with the number of clusters K and look for maximum separation between the clusters. All right. So why do we need clustering? If you have high dimensionality, thousands of features, let's say in a data historian, it's not feasible to include all of them for modeling. So when you have high dimensions, similarity versus dissimilarity, we want to segregate samples into groups that are alike and samples that are not alike, right? So you want to be able to, there are problems where you want to do this. And pattern recognition, we also want to identify key features or characteristics between groups that are alike. These clusters can also provide sometimes process insight or knowledge. You can develop mechanistic rationales for seeing what you're seeing in your data set. Okay. There is another very popular clustering algorithm called hierarchical algorithm. This is what I want to skip, but I encourage you to read through these slides. I'm going to give you the slides, so please go through these slides. You'll also find a lot of information on hierarchical clustering. And then the way it works is there's a picture here that sort of explains. There are different ways you can have agglomerative clustering or divisive clustering. In agglomerative clustering, you start with all your samples, and then you have some sort of a similarity matrix, and you start grouping things that are similar, and then you keep doing that repeatedly until you aggregate everything. Right? So that's you can stop at any level. At different levels, you have different number of classes. Right? So that's one way. Divisive clustering involves going the other way around, where you start with all your data, split it into two clusters, and then you keep splitting it further using a metric that determines the variance in each of those clusters. Okay. So I know I'm doing a little bit of hand waving here, but that's there are good slides here that you can go through. Okay. So with that, I want to wrap up clustering as well. Are there any questions? So we finished clustering, classification. In the next 1 hour or so, we're going to talk about dimensionality reduction. Any yeah. Sorry, good. Yeah. I can hear, but I'm not sure if others can hear.
Hello?
Yeah.
Yes, sir. So does the accuracy of these algorithms, clustering algorithms, depend upon how many number of clusters it can easily predict, or how it is evaluated?
Right.
Physically, I want to understand, not mathematically.
So you're saying the accuracy, how do we determine whether you have the optimal number of clusters or not, right? I think it goes back to an earlier question before in the last session. You can use the size of these clusters as a measure of whether size and the variance within each cluster, right? As a measure of whether you have the right number of clusters or not. There may be other ways of measuring the performance of clustering, but that seems natural to me. So, for instance, if the variance of some of your clusters is really large compared to the others, then maybe there's an opportunity to split those clusters into smaller clusters. Then you increase the number of. I believe there are certain information criteria. I don't remember the exact criteria that you can use to find the optimal number of clusters. Right? Have you heard of a Kaike information criteria? No. Okay. So that's widely used in assessing the quality of models, where it's a criterion that depends on the model error as well as the number of parameters. So if you increase the model error or the model parameters, then the criterion value also increases. So there is a sweet spot between the model error and the number of cluster and the number of parameters. Okay. I think something similar to that can be used with clustering. So that gives you some sort of a sweet spot for a number of clusters. Okay? Yeah. Those are your features. They're not clusters, right? So they are features. I mean, each measurement in that case would be temperature, humidity, and something else. Sorry, wind speed. Yeah. So that would be one measurement, right? And that is that's a single data point. That's not a cluster, the way I see it. That makes sense? So those are measurements in 3 dimensions. Now a cluster would be a cluster of those measurements, a cluster where the temperatures are similar, the humidities are similar, the wind speeds are similar. Right? So that would be a cluster. That is across dimensions, right? So why do you say it's within a dimension? So I think what he's asking is, can you just cluster within a dimension? That's no. So okay. Okay. I think that's a good example. Let me see if I can draw a picture, 3-dimensional picture, and we can understand. We'll try to understand, or maybe 2-dimensional picture. We'll just take temperature and humidity. Okay. So I'm going to how do I? So all of these have the same humidity, and then so I think what you're saying, if you try to cluster all data points of the same temperature, then you would see this cluster, and then this cluster, right? But that's not really what we're trying to do. We're trying to find clusters. Okay, so let me take and let's see if I can construct a more extreme example. Yeah. Okay. So I can see. And then. Okay, so let's say these are my data sets. There are 2 natural clusters. So there's one over here, there's one over here. But if you try to put all samples with the same temperature together, then you have this cluster, and then this cluster maybe, and another cluster like this, right? But that's not what we're trying to do. We're not trying to find clusters within a dimension. We're trying to find clusters across all dimensions. In which case, this is a natural cluster. This is another natural cluster. Does it answer your question as well? Yeah. Okay. So I think some of you said you've learned dimensionality reduction, right? So can somebody explain what you understand by dimensionality reduction? What tools have you learned? What is dimensionality reduction?
So it is about removing the less important features in the data set and
Right.
using the only important ones to fit the model. So that is dimension reduction. It improves the processing time. So we're learning the PCA, the principal component
PCA,
analysis.
right.
And we use the variance to determine which is the more important components. And on the basis of variance, we fix the components first or second, like that. So.
Right. Yeah. So typically, when you're dealing with industrial processes, you have lots of variables, lots of dimensions, and often there is redundancy in the data. Right? So for instance, you may have 3 temperature sensors on the same same process. Or you may have multiple flow sensors on the same process. And when you collect data, you have all of this data, but the information in some of these measurements is similar. It's sort of duplicated in those measurements, right? And if you use those high-dimensional data and try to build models, you can sometimes run into issues around singularity of inverting matrices, etc. Okay, and sometimes you want to visualize your data in lower dimensions. If I have 10 dimensions, it's difficult to visualize it, right? If I can plot the same information in 2 dimensions, then it's much easier to visualize it, right? So one example where dimensionality reduction is used, it's a very commonly used example, is in process monitoring. Okay, so you have, let's say, a couple of variables, x1 and x2. They need not be the true variables. They are probably variables in the reduced dimensions. So you have, let's say, 5 different variables. You reduce the dimensions, get them into 2 different variables. You can plot these variables in 2 dimensions and observe your process. If there is something that breaks down with your process, the underlying system dynamics, then you will notice that these data points move to a different location in the lower dimensional plot. Okay, so that tells you maybe something has gone wrong with your process. Now, if you're trying to monitor these variables in the original space, where you probably have 5 or 10 different dimensions, it's not possible, right? So if you have 10 dimensions, you cannot visualize 10 dimensions on a piece of paper. But if you reduce the number of dimensions, it's much easier to visualize. Okay. That's one reason dimensionality reduction is used. Dimensionality reduction is also used in modeling. Instead of building a model with all your 10 variables, you can build with just 2 or 3 variables. It's a lot more efficient. Your model is going to be parsimonious. Okay. So what is dimensionality reduction? It's the process of reducing the dimensionality of your feature space with consideration by obtaining a set of principal features. You have D features, you reduce the number of features to something to a set of features that capture the variance of the original set of features, but there are fewer of those. So here's a visual depiction of what happens if you have n different features. Okay, you select just a subset of those features. You skip those, and then you can extract modeling features, etc., using the subset of those features. So some of this is going to be clear as we go through principal component analysis. Principal component analysis is a very popular dimensionality reduction algorithm. It's a linear algorithm, but there are some nonlinear algorithms as well. I'm going to very briefly allude to those nonlinear algorithms. So why is dimensionality reduction important? You've given me some examples. If you have too many dimensions, you run into this concept of curse of dimensionality. Sample density increases in very high dimensional feature space. For example, if you have 100 samples in one-dimensional space versus 100 samples in a space of 100,000, the sample density is going to become much smaller as you increase the dimensions. Right? So if you have a really large dimensional space, you need exponentially large number of samples to solve your problem. Okay. So if you have 100,000 dimensional space and only 10 data points, that's a very small amount of data. On the other hand, if you have a one-dimensional space and you have 10 data points, that's probably a reasonable amount of data to perform other machine learning exercises, right? So that's called curse of dimensionality. In higher dimensions, you need more data. Dimensionality reduction also helps in selecting relevant features. reducing the number of parameters in your model. If you're not using all the dimensions, but a reduced number of dimensions, you can reduce the number of parameters, which means you can have a parsimonious model. In computations, when you have fewer features, obviously you can improve computational time, and sometimes you can also improve model performance, okay, using dimensionality reduction. There are several methods for dimensionality reduction. There are linear methods, nonlinear methods, non-parametric methods. And these methods either preserve local or global properties or structures in the original and reduced databases. They're different for regression, classification, and visualization problems. Depending on the type of problem that you're trying to solve, you will pick a different dimensionality reduction tool. So I want to go back to a block diagram that I drew yesterday. We have, I talked about different steps, right? Data collection, data pre-processing, and then I had modeling here. Dimensionality reduction really comes in after data processing. Dimensionality reduction, and then you model. Okay. So there are two different types of dimensionality reduction algorithms. One is linear dimensionality reduction. The other is nonlinear dimensionality reduction. PCA falls under linear dimensionality reduction algorithms. So how does PCA work? Let's suppose that you have very high dimensional data and that we are dealing with a regression problem. You're interested in reducing the number of features while preserving the overall variation in the data. And that's exactly what PCA tries to achieve. Let me draw a picture that explains the idea behind PCA. Not sure if I have the picture here. So let's suppose I have some three-dimensional data. Three axes, x1, x1, and the data are on a hyperplane in the three dimensions. My data are they're on a hyperplane in three dimensions. Now, to describe this data, we don't really need three axes or three dimensions. That's the whole idea behind PCA. Right? Obviously, in practice, some of these data are probably going to be close to this plane, but not quite on the plane. Now what I can do is I can rotate these axes. The three axes I have here, I can just rotate them. In such a way that the data are now on a two-dimensional plane. There is a third axis. Third axis goes like that. Okay. Sorry, my picture is probably not very clear. So the way to think of it, so let's say this is your plane in three dimensions, right? Now you're seeing this one here in three dimensions. Your data fall approximately on this plane. But if you rotate your axes, you can find a position where this plane is actually on a two-dimensional plane, like this. Right? So initially it's like this in 3 dimensions, but then you can rotate your axes and bring them, position them in such a way that the plane lies on a two-dimensional space. Okay? Because this is a two-dimensional space, in a sense, in 3 dimensions, where you can rotate the axes and place it on 2 dimensions. When you do that, you no longer have x1, x2, x3 as axes. You have some combination of x1, x2, x3 on each of these axes, right? Translation and rotation of these axes. And those combinations are called principal components, PC1, PC2, PC3. So in this coordinate system, what is the coordinate of each of these data points in the PC3 direction? Sorry? 0. Yeah, it's 0 because all of these data points are on PC1 and PC2. So once you transform this, every data point will have some PC1 value, some PC2 value, and then no PC3. PC3 is always 0 because it's on a two-dimensional space. Okay. Now you can imagine the same data set where there are small errors. Okay, the data are not exactly on this plane, but they're slightly away from the plane, where they're in different directions, right? And when you rotate this, you will still have these data points approximately on the two-dimensional space, but you will also have some PC3 component or coordinate. Okay, it's not going to be 0; it's going to be a small value compared to these 2 other principal components. Okay. Now, the idea behind principal components is basically to rotate these axes in higher dimensions in such a way that the maximum variance in the data is concentrated in the first few coordinates. The rest of the coordinates have very small values or small variance. That's the basic idea behind principal components. Now we have to do this mathematically, right? So how do we find these principal components? How do we optimally rotate these axes so that the variance of the data is captured in the first few principal components, first few coordinates, and the rest of the coordinates have small variance, right? How do we do that? There's a bit of simple math involved here, some linear algebra. Some of you are probably familiar with this. PCA is a popular dimensionality reduction technique for regression. It's based on feature extraction. It provides a compression of original data x of dx dimensions into zx of k dimensions. So our original data is in this matrix X. This is the big matrix. You have n samples and dx original features. We want to reduce the number of features from dx to k. You're still going to have the same number of samples. And to do that, you have to rotate your axes. That is equivalent to multiplying the data matrix with some other weight matrix wx in order to get zx. Okay. Now you have to find this wx, the transformation that takes you from the x space to the principal component space z. How do you calculate wx? It's calculated such that the variability in x is preserved in zx. Okay, so you try to preserve the variability of or the covariance of these 2 matrices, the original matrix X and the transformed matrix Z. Yeah, this is the same concept that I tried to explain here in 3 dimensions. This picture is doing it in 2 dimensions. Okay. Would you like to know how that W is calculated, or the principal components are calculated? I can go through the math involved. So let me do that here. It's very important to standardize the data. We talked about standardizing the data. In PCA, you have to make sure your data are standardized before you apply the algorithms. The first step is to standardize. So I need my reading glasses when I'm near the board here. Okay. So the first step is to standardize the data. Standardized data, meaning remove the mean and divide it by the variance. And let's assume the standardized data set is the following. It's x tilde, capital X, that is, equal to x1 tilde first dimension all the way to x tilde dx. That's the dx dimension. Okay. The third step is we calculate the data covariance. It is denoted by sigma, which is equal to 1 over n x transpose x, or x tilde transpose x tilde. Okay, standardize the data, then calculate the data covariance. Now, this covariance matrix can be expressed as follows. Where we've used something called singular value decomposition. Are you familiar with singular value decomposition? Yeah, you are familiar. So you can write any matrix in this form where U and W are orthonormal matrices. And this lambda is a diagonal matrix. Okay. So this type of decomposition is possible using singular value decomposition. What is an orthonormal matrix? If W is an orthonormal matrix, therefore W transpose W is an identity matrix. Same is true with U transpose U. Is also an identity matrix. Now I can simplify this further. So I get 1 over n. The simple matrix algebra. If you don't understand something, let me know. Now this is by definition an identity matrix. Therefore you can simplify this further. 1 over n W and this lambda square is a matrix of eigenvalues of the covariance matrix. Okay, so that's the covariance matrix. And this lambda square here has eigenvalues along its diagonal. Then the first principal component 1, is the vector W1, which satisfies the following equation. It's the eigenvector of the covariance matrix for the largest eigenvalue. Okay, this is the eigenvector. Lambda 1 is the largest eigenvalue. Okay, this is the covariance matrix. This W1 is also the first principal component. The vector W1 is the first principal component. Okay, so you can repeat this for other PCs. W2 corresponds to the second largest eigenvector, and so on and so forth. Okay. And each of these principal components, they capture some variance of X transpose X that is proportional to the corresponding eigenvalue of that principal component. So in other words, lambda is a measure of captured variance by that particular principal component. Now, if I were to plot the variance captured by a principal component, sorry, and the principal components, PC1, PC2, and so on, the first principal components capture quite a bit of variance, because the variance captured by each principal component is proportional to the corresponding eigenvalue, and you're going in the in your principal components are essentially the eigenvectors corresponding to the eigenvalues in the decreasing order. So as the variance explained by the principal components decreases as you go down your list of eigenvalues. Okay. Now there is often a point beyond which there is no need to include your principal components. In other words, you can capture the variance of your data using the first few principal components and ignore the others. Okay. Now imagine you can correlate with the pictures that I drew in 3 and 2 dimensions. In going from 3 dimensions to 2 dimensions, you're using only 2 principal components to explain all of the data. The other principal components are not needed to explain the data. Okay. There is going to be an error for sure when you drop some of these principal components. But that's the idea behind dimensionality reduction. You want to reduce the number of your dimensions without losing too much variance. Okay. You gain in terms of lower dimensions, but the loss is there are going to be small errors between the original data and the data in the reduced dimension. Now you can use Iris is a popular data set of flowers. It has 3 different classes. You can perform PCA on that data set. You can once you have these lower dimensions, you can build a classifier in the lower dimensional space. That's the example on the left-hand side. The example on the right-hand side is PCA performed on digits data set. You've probably heard of MNIST data set. There's a data set that has, it's a very popular data set that has handwritten digits from 0 to 9. So there are 9 classes. You're supposed to separate those 9 digits using a classifier. Now here, we've done PCA on that data set and are hoping to find the 9 digits in separate classes. Right. The problem is with the Iris data set, after dimensionality reduction, you can very clearly see different clusters. Right. So therefore, you can apply the clustering algorithms, one of the clustering algorithms, to separate them. But with this data set, the digits data set, there are no clear clusters. Right. or there is no way to classify these different digits. They're all mixed up, and it's really hard. So linear dimensionality reduction does not work well on the digits data set, whereas it works well on the iris data set. Linear dimensionality reduction, linear discriminant analysis. I will, and I want you to spend about 15 or 20 minutes working on the code with the dimensionality reduction. So I'll go through some of these a bit faster than normal. Is that okay? But you can, of course, read through the slides, and there is also a lot of material online. I'll give you the basic idea behind linear discriminant analysis. This is a different dimensionality reduction technique. The idea here is, in this example, we want to find, this is a two-dimensional data set, and we want to reduce the dimensions to 1. Okay, so I want to reduce the dimension to 1. And the way I want to do that is by finding a straight line such that when I project these data points onto that straight line, I get very clear separation between different classes in the data set. If you look at this data set, there are 3 different types of data. I think crosses, circles, and triangles. I want to find a straight line by, do you know what projection is? It's basically the shadow of your data on a certain line. So I want to find a straight line in the space so that these 3 data sets are maximally separated. And it's easy for me to use a classification algorithm. Right? Now, I have 2 examples here. If I find a line over here and then project all of this data onto this line, you will see a mixture like this. Okay? Now, that's very difficult to separate. Right? So you can't find boundaries between different classes, and this is not an ideal straight line. Right? But on the other hand, if I choose this straight line and I project them onto this straight line, I have clear separation between these 3 data points. In linear discriminant analysis, the goal is to find this hyperplane in a higher dimensional space. This is 2 dimensions, so easy to visualize and understand. In higher dimensions, we want to find this plane such that it gives you the best or the maximal separation between different classes that are in the data set. Okay. So this is another linear tool for dimensionality reduction. Okay, so there's a little bit of math here, which I'm going to skip. And then here, the iris data set, again, what you see on the left-hand side is PCA. What you see on the right-hand side is the linear discriminant analysis. Both of them perform reasonably well on this set, PCA. And again, on the digits data set, PCA performance is really bad. On the LDA, is slightly better, but it's still not great, right, for classification. Okay, now that being the problem, so there are lots of data sets where you cannot use linear tools for dimensionality reduction. You have to use nonlinear tools. So that's where nonlinear dimensionality reduction comes in. There are lots of different ways of nonlinear dimensionality reduction tools. TSNE, Salmon mapping, isomap, LLE, kernel PCA, Laplacian eigenmaps, etc. There are quite a wide range of these. TSE, and there's another new method called UMAP. We found that those methods work really, really well when you need nonlinear boundaries to separate your data. TSNE is one of those award-winning algorithms that was designed for visualizing high-dimensional data set It maps multi-dimensional data to 2 or more dimensions suitable for human observation. It's one of the state-of-the-art methods in dimensionality reduction. It's more effective than a wide range of linear or nonlinear methods, and we found that it works really well in practice. Okay. Now I'm going to do a little bit of hand waving here, and I apologize because we don't have time to go through all of these algorithms. But I want you to be aware of some of these algorithms, TSNE. At a very high level, the way it works is in the high dimensional space, it creates a probability distribution that describes the relationships between various neighboring points. It sort of defines the distribution of points in various neighborhoods. And it tries to create a lower dimensional space that follows more or less the same distribution. Okay. So for instance, if you have Gaussian distribution in the higher dimensions, it'll try to create a lower dimensional Gaussian distribution. Okay. And it's an approach that preserves local relationships between neighboring points in both high and low dimensions. Meaning, if there are 2 points that are close in some sense in high dimensions, they're also going to be close in the lower dimensions. Okay? It's not going to jumble the data up and move it in different directions. So that structure, local relationships, are maintained in dimensionality reduction. Okay, I'm going to skip some of this and go directly to my example. So PCA digits data set, you've seen this before. LDA, slightly better on the digits data set. Now let's see what happens when you use TSNE, right, on digits data set. The separation between different classes is much clearer, much more clear, right? So TSNE is a very powerful tool. We've used it quite a bit, and it works really well. While PCA is widely used, TSNE is probably the state of the art. PCA is deterministic in the sense that when you go through this process, you have your PC's principal components are all deterministic, whereas TSNE is stochastic because you're building these distributions. PCA preserves the global structure. TSNE, as I explained, it preserves the local structure in your data. So PCA gives you an expression for each of the principal components, right? So you have a function to work with. On the other hand, TSNE, it does not learn a function. There is no function. You provided the data, it just gives you the lower dimensional space. But there is no, in PCA, you have an explicit relationship between higher dimensional space and lower dimensional space, right? So if you remember in my slide, I had Z equal to X times W. This is your relationship between higher dimensions and lower dimensions. That's the relationship. Whereas with TSNE, this type of relationship is not possible. You go through an algorithm and you generate your lower dimensional space, and there's no explicit function that relates lower and higher dimensional spaces. PCA is fast. TSNE can be a bit slower than PCA. And finally, UMAP it's called Uniform Manifold Approximation and Projection. That's also a very powerful dimensionality reduction tool. We've tried both TSNE and UMAP. They seem to work far better than PCA in many applications. Okay. Just like TSNE, it preserves global properties as well as local properties. It is computationally faster than TSNE. Okay. All right. So those are all the slides I have on nonlinear dimensionality reduction. So in the next 20 minutes or so, if you don't mind going back to the Python notebooks, and then click on dimensionality reduction. There is a Python notebook with some instructions on how to do dimensionality reduction. Yeah. You might, if you like, you can download the digits data. It'll be fun to try it. Digits data. But try it with the data that's in the folder. If you have time, you can try other data sets or iris data set.
Hello, sir.
Yeah.
So, sir, there is a question regarding the data set itself. Let us say we have a data where there are some features which have a numerical value, and in that feature also we have some categorical thing, such as yes or no, something typically we get
categorical data. Yeah.
sometimes we get with a health, lifestyle, something like
Right.
that. And then you have a one feature, that is it's a,
Right.
you are healthy or not,
Right.
something like
Right.
that. So how to use such data to do some, model fitting or, some coming up with some classification, something like that, because you have numbers and the categories also. How to pre-process or how to play with such data.
So can you give me a clearer example?
So let us say, yesterday I downloaded data from kaggle.com. So it's a lifestyle. So it has a height, BMI, age,
Right.
sleeping hours, then smoker or not, so yes and no, then something like that. Let me.
Yeah, yeah.
So there are two or three categorical features. Then you have a one. We can. It does not specify the one output level, but there is. We can make let us say
Some
stress
inputs
level.
are categorical.
Yes, sir, some inputs are categorical.
And the outputs are all categorical, or
So it hasn't been mentioned that, but it has given a data frame where their stress level are also mentioned.
Right.
So I'm presuming that let's my stress level will be output
Right.
level. So more kind of classification problem.
right?
So how to handle such data or what sort of pre-processing
Yeah, I
that
mean,
we
you
do?
can, so let's say you have a time series data. One variable is just time series, and the other variable is categorical. You can, the first thing you want to do is normalize the data. That's, I think, is going to be very important. You don't want to have a category that's 1 million, another category that's 2 million. You don't want to have stuff like that. But once you categorize the data, you can use it with the traditional approaches, right?
Okay.
I'm trying to see where you might encounter problems. So let's say you're building a regression model. Then you yeah. So let's say you have x1, x2, two features. X1 is time series. X2 is categorical. And you want to build a model alpha 1 x1 plus alpha 2 x2, and then that gives you some variable. You can build that type of model. Yeah, I don't see any obvious challenges.
Okay.
But is there something that you found that it doesn't
No,
work?
so how to incorporate that category in the model itself, sir? It's a yes or no. Simple.
Oh, I see. Okay. Oh, okay. So I see. I get what you're saying. You have to assign. I was telling somebody else also. With machine learning, you're always working with numbers, whether it's large language model or images or something else. You always have to take your data, whatever it is, and turn that into some numbers. Okay. So if you have yes or no, then you're going to give yes 1 and no 0.
Okay, sir.
Right? So you always have to, if you have 5 different categories, then you can go from -1, -2, 0, 1, 2, or you have to always turn those categories into real numbers. Okay, sorry, I probably misunderstood
That's
your
okay, sir.
question.
So only one, how to handle those categories.
Yeah,
So
you have
converting
to
them
add
into
categories.
numbers.
Yeah.
Thank you, sir.
Somebody asked me to talk about transformers tomorrow. What do you call the language models, right? So I was explaining it to a couple of students earlier. Every word it has a unique vector representation, right? Every word, they're called tokens. They don't actually use words. They use tokens, which are smaller parts of words. There is a function in MATLAB, and maybe available in Python as well. It's called word-to-vec. Every word has a unique higher dimensional vector representation. Okay. So I think in English language there are 70 or 100,000 words. Every word has a unique representation. Right? Now, if you think of a word, if you think of a sentence, the sky is blue. Okay. the sky is blue, they all have a vector numerical representation, right? The sky is often followed by blue. So if you think of it as a time series, where each word is a vector, higher dimensional vector representation, there is that correlation between between consecutive words, and there is you'll find that correlation between consecutive vectors as well from in the data. So that's how the word and text data are used to train these large language models. So the models are always working with numbers. You always have to figure out a way to transform your whatever data you have into numbers. Yeah. Yeah, we might be able to do that. What type of process is it? Uh-huh. So if he can generate an Excel spreadsheet, they know how to do all the clustering, classification, all sorts. For instance, he can introduce a fault into the system, and then generate data, generate normal data as well. Then they can use those two data sets to do clustering. They can, yeah, they have a Python notebook that explains how to do it. Yeah. So how is it going? Did anyone, did you finish it? Are you very fast? Did you, if you're done, somehow I'm not able to access internet, but search for iris dataset. And load it, and then you will see the plots that I generated. Iris dataset, or the digits dataset. Yeah. Look, yeah, I see. Okay. Yeah. So there's actually a nice picture. It's called Swiss roll. So let me use that to explain. Okay, so this isomap, this data set, it's called a Swiss roll. Okay. Now, when you that data are in 3 dimensions, right? Now you can imagine unrolling the Swiss roll. Okay. So when you do that, you want the neighboring data points to stay closer in your lower dimensional space. Okay? So, for instance, there are these blue data points that are over here. Okay? When you unroll it, when you go to the lower dimensions, you want all of these blue data points to stay close. Okay? You don't want them to sort of show up in other places in the lower dimensions. So that is what is preserving the local features of the data set. Okay? The global features are, it's sort of opposite of that, right? there is this distance between these points and these points. If you look at this, the actual distance in the 3 dimensions is really small, but in the lower dimensions, it's larger, okay, because of the way the data are arranged. So you want to maintain the local features as well as the global features as you're trying to find these lower dimensional spaces. Does it answer your question here? Is everyone done? Yeah? It's very fast. With Gemini, that's why we don't need coders anymore. You can, as long as, I think the key things are, you need to understand the problem you're solving. You need to know how to formulate the problem, right? Coding itself is very easy. Sometimes in some of these algorithms, there are tuning parameters, hyperparameters. Python or Gemini won't tell you which hyperparameters to choose. For instance, in the morning, I think it was you had neural networks. You probably use default number of networks and default activation functions, etc. You have to understand what those hyperparameters are and how you can tune them in the code. Gemini will not tell you how to tune it, right? So. Okay. Any other questions? Final questions before we wrap up. Tomorrow, I'm going to do regression in the morning, okay? And then we will do reinforcement learning and a little bit about transformers. I don't have a lot of slides on transformers. I'm not sure. Was that you who asked for transformers? Yeah. So we'll talk about transformers a little bit. Yeah. Sorry? Right. Yeah. So I'll talk about transformers as well a little bit. Yeah. I might just use the board for transformers. We'll do regression, reinforcement learning, and transformers. With reinforcement learning, I will introduce you to something called OpenGym that has lots of models that are available. And I don't have code, but I would like to challenge you to use Gemini and build a reinforcement learning algorithm tomorrow. So there's something called a moon lander. You can build code to land it. Moon lander, OpenGym. Somehow I can't get the internet to work here, Google. Anyways, we'll do that tomorrow. OpenGym is an online website where there are lots of different types of models available that you can use to build reinforcement learning type of algorithms. Yeah. I don't think I compared UMAP and TSNE. Yeah, I compared TSNE and PCA and LDA, linear discriminant. I'm not entirely sure. You can choose always if you have flexibility. You can always choose 2 dimensions, but is that going to capture the true nature of your data? That's a question, right? So we don't know if we can do that always. It depends on the type of data. Okay, it's 1 o'clock, so lunchtime. If you have any questions, we can chat again this afternoon or tomorrow. Is there any other topics that you would like to see tomorrow? Regression. If we cover regression and RL, we've basically covered the entire spectrum of machine learning, not tools, but the problems, right, at a high level. Sorry? Regression is same as curve fitting. So it's basically about finding a function that relates your inputs to outputs. Okay. Have you heard of Gaussian processes? Yep, so, okay. We'll talk a little bit about Gaussian process and a few other standard regression types. Okay, thank you.
The electrical vehicle will be there. We just take the electrical vehicle.
So what's the schedule tomorrow? Sorry, we said. Yeah. Okay, so here we have some meetings. I don't know how much time I will need. So if I go a little bit into
Today you want to take it?
tomorrow is better. I have to get my stuff ready. So my flight is at 6. So, and you have and we're meeting the director around here lunchtime. Okay. So we'll start at 9:30. I think we'll be fine. Yeah, I should be able to work out. No. The goal is to not lose information. Minimize, or the goal is to minimize the loss. We're not. So that's two dimensions. I had it. That's your name. When you rotate your axis, now if you want, then you can sort of project these into this axis. But because you're projecting that, there is a bit of an error. If you only use the idea behind analysis is that when you rotate the axis in the right way, what you're losing, the errors are going to be very small. Does it make sense? The errors are small. So if you take each of these coordinates of these points, PC1 will be large compared to PC2. PC2 is going to be very small. And what you're doing is you're setting this to 0. Then you only have PC1. Now when you set it to 0, obviously you're incurring a cost. And that's actually that's negative. But that's the downside. You incur a cost, but then the upside is you have fewer errors. Makes sense. Yeah, I've left you the room. Are you familiar with all of this stuff?
I know the round of applause.
Kind of.